this is the second part of our discussion on regression. So in the last video, we figured out what our regression equation is. So the next step is kind of figuring out what does it. So that's what we want to know. We want to know about interpretation of the regression analysis, and we want to know something about prediction as well. So what does this model mean that we've tested, and how well does this mathematical model, our equation line, our regression line, do in predicting our dependent variable? So first, let's talk a little bit about understanding what our regression equation means. And so there's one measure that we can use. Your textbook doesn't talk about how to compute this. You would get this from statistical output. But the standard error of the estimate is like a standard deviation for the regression line. And what I mean is it gives us a sense of how far away, on average, our data points are from that regression line, which is also our line of best fit. So it's the typical distance between the regression line and the actual data points. So here is an example to kind of think about this conceptually. Which of these two graphs makes a stronger prediction, and why is that so? If you said graph A, you'd be correct, and the reason is because the data points are closer to this line on average than they are to the lines, or to the regression line in B. So if your data points are more tightly clustered in around that line of best fit, then what you've got is a stronger prediction. Another concept that comes into play when we talk about regression is regression to the mean. And basically what this is that our extreme scores, so really high scores or really low scores, tend to bounce back or regress to the mean of that particular set of scores. So any extreme scores we have, when we make a prediction about what that y would be based on what we know from x, our predicted y tends to be closer to the mean than our actual extreme y scores. So the ones that are kind of out there at the far ends of the distribution, really big or really small, the prediction that the regression equation will make is going to be closer to the mean of those data. So here you can see if you have the z-score for an independent variable x, what is that predicted z-score for the dependent variable y? Right? Here's a -2, and look, it's a little bit smaller, 1.7. -1, it's 0.85. 0, well, it's going to be at the mean. +1, -0.85, and +2, -1.7. So you'll see that they tend to be closer to the mean when you have your prediction than what you have for your actual scores. You can see another example here. When you look at stocks, the highest stock, it regresses towards the average and it gets lower. The lowest stock actually does better the next time they make a measurement. So that's also an example of regression to the mean. So this last part has to do with how well the model fits. And we can look at that by examining the proportionate reduction in error. It's also called the coefficient of determination. So what it tells us is how much better our predictions when we use the regression line instead of the mean. Okay, so we're essentially comparing this formula when we predict y based on the intercept and the slope and what we know about x, versus if we were just going to predict y based on the mean of the y scores. So which one's better? So here we have an example where we've got grades for students and we are predicting exam scores. We know the average grade. We know how far then each grade is from the mean, and then we square those. And you know, we've been doing this all along whenever we've been computing the variance or the standard deviation, and that's what we're talking about when we're talking about that model. This would give us a sense of the total sums of squares. So how far are each of these data points off of the line that indicates the mean of our distribution? So some people, oh look, this guy didn't do very well on his exam and he skipped 7 classes, but then we have somebody else who skipped 8 and they did a little bit above average. And we've got people who, you know, here's somebody who missed 2 classes and did at the average, and then somebody who missed 2 classes and did really well. So we've got some people that are higher or lower. Okay, so that's what we're talking about with this mean here. So that's the first thing that we're comparing, and we're comparing it to how much better our prediction. So we substitute x into our regression equation, and we get y hat. So we want to find how good this predicted value is based on what we actually have for y. So we can actually compute error scores and square those. And so we can actually say we have squared error. So the sums of squared error would tell us how far on average each of these points tends to be away from our line of best fit or our regression equation. And it does look like it might be a little bit better here before we actually calculate it. Here we have another example. And so we've come back to the data that I was using earlier with the scatter plot for height and weight of children who are between the ages of 0 and 4. And we have, we're going to calculate the proportionate reduction in error. So we use, you know, this first regression equation to compare to, right here, see we put that line in. And here's our regression equation that we calculated last time. Our intercept is -15, so somewhere down over here. And for each inch that the child grows, they gain 1.219 pounds. Okay. So our other comparison is going to be if we use just the mean of y to predict what y would be. And so we'll put that line in here as well. So we have the mean of y is 21.5. That's our average weight of all these babies and young children, 21.5 pounds. And so we're saying, okay, which of these two lines has all those dots closer to it? Now you should be able to tell just by looking at this that we are going to expect that our reduction error is going to be really big here, because these data points, if we were to draw in the lines, would be really far away. So we're going to start with calculating the sums of squares total, which again you've done before. In fact, we did this when we calculated the correlation coefficient. But we're trying to figure out here how far are each of these data points, right, from the mean. So I could draw some of these lines in here and say, oh, look, these are pretty far away. I'm not the best at drawing with a touchpad mouse, but hey, you can see that these lines are going to be further away. Right? You get the idea here. Okay, so we're going to check the next slide here. So if we were going to calculate the proportionate reduction in error, then what we'd want to do is, I don't think you can see all of this, here we go. All right, we have our mean of 21.5 pounds. We're going to subtract out for each individual score the mean of y, and then we square those values. So you might want to pause it now and see if you can compute the sums of squares total. Okay, so here are all the values if you want to check your work. And the sums of squares total for this model ends up being 1,388.3. So the next part is that we need to find the sums of squares error. And what we're doing here is saying, okay, well, how far are all of these red dots, our data points, from our regression line? And, I barely have to draw a single thing to get these guys connected. So you can imagine this is a really good fit. So what we're saying is, what proportion do we reduce the error variance by when we add our knowledge of x? And so in this case, we're going to expect that we're going to reduce the error. The proportion is going to be pretty high. It can go all the way up to 1 if you perfectly reduce it. Now this isn't perfect because we don't have all of our data points exactly on that line, but it's going to be pretty good. It's going to be pretty close. So what we need to do is take our y-scores and subtract out that predicted y. So where do we get that predicted y? Well, we use our regression equation, and for each of our x's, we substitute in that value, and we get, well, I didn't put the x's back in this, but it is in the previous video. We get these predicted values here. Okay, so now we take the y hat and we subtract out. We take the y and we subtract out the y hat, so our weight, subtract out our predicted weight, and notice again what we were talking about, regression to the mean, 28 pounds, oh look, 27.9, 26.1, it is a little bit smaller. Okay, so we do that, we square those values. You can pause now and do the calculations yourself and start it again and check your answers. Okay, so once we finish getting all of these squared errors, then we can add them together and we get 14.09. So that's our error. That's how much variability we're off by in terms of that line. Okay. So in order to compute the proportionate reduction error, what we do is we take our sums of squares total and we subtract out the error. And what it gives us is how much of our variability is accounted for by the model. And it's easier to do it this way because you could do this with a multiple regression and you wouldn't have to figure out, well, how much for this predictor and how much for the next predictor and how much for the next predictor. All you have to do is find the error and subtract it from the total, and then you find that proportion. So what percentage of the variability in y is accounted for by knowing something about x. So if we substitute in our values, we find that our r squared is 0.99. Its proportionate reduction error is also known as r squared, which is also something that we see in analysis of variance if you think back when we're talking about effect size. So I think that's pretty interesting because remember, sums of squares between, which is kind of what goes on up here because we're saying, oh, everything that's not error divided by the total sums of squares. So there is a relationship here. Okay, so that brings us to multiple regression. And I mentioned it earlier, it is a statistical technique that includes two or more. So what we have here under the model is our intercept is the constant, right, for our unstandardized regression equation. And then we have our two x variables, number of absences and SAT. And these are the slopes, they're partial slopes for number of absences and SAT. We also have our standardized regression coefficients, and we would report these. This one is beta 1, this one's beta 2, and we can then look at our significance right here. They're both less than 0.01, so they're statistically significant. This says that essentially the intercept is significantly different from 0, so you can kind of ignore that top one because we know 33 is significantly greater than 0. But even though this standardized or unstandardized coefficient is really low, the standardized coefficient is pretty high. These are the ones we want to examine, and this gives us more telling information. So this is where we want to focus.